Right guys, so we have gone through a basic FE problem for two collinear springs. So let's just have a reminder of how we set up the problem. We said we had three nodes connected by two springs. So we said two stiffnesses K1 and K2. We have global nodes 1, 2 and 3, and each of these has an associated displacement Q3, Q2 and Q1, and if they're global they are uppercase. And we could also apply forces here, so F3, F2 and F1. And we, in the preceding lecture, had looked at a single spring and said that for a single spring that has stiffness K, it has a local, so let's do this in yellow, node 1 and node 2. So our spring will always have node 1 and node 2. Okay, so for this element, element 2, this is its local 1 and its local 2. Okay, so we then defined these lowercase forces and lowercase displacements. And we said that for this setup here, we showed that the stiffness matrix would be KK, minus K and minus K, Q1, Q2 is equal to F1, F2. And so this was KE, QE is equal to PE. Now we were able to set this up for this problem. This is always going to be the shape for a spring element. We were then able to recognize that for these two different elements, let's say up here we've got this is our general expression. We then said for this first element, let's draw in a different color so I'm not overusing that green. We said for element 1, we had K1, K1, minus K1, minus K1, Q1, Q2. We had to recognize that these belonged to element 1. These were the local Q1 for element 1, local Q2 for element 2. And then the same here, force 1 for element 1, force 2 for element 1. We did the same thing over here, K2, K2, minus K2, minus K2, Q1 for element 2, Q2 for element 2 is equal to F1, 2, F2, 2. Okay, so let's just write this was for element 2. Now the next step was to say, well, we can't combine these together yet because we've got Q1, Q2, Q1 and Q2 in here. We could recognize that Q11 is, it doesn't move around, Q11 is this one up here, which is Q1. I haven't actually got that written on there. Let's say that's Q1. And Q21, no, sorry, lowercase, recognize that this one here, it's local to the second element for, sorry, the second node for element 1 be Q2. There we go. We could also recognize that over here we've got Q1 of element 2. That is this node here, which is Q2. So Q1 of element 2 is Q2, and Q2 of element 2 is Q3. So we could replace these in here. In fact, let's just do that. Let's get rid of these. Okay, so we've represented these now. We've now got global coordinates here, but we can't add these together yet because these need to have the same vector in order to add these matrix row equations. So we then just expanded them. We said, let's expand this bad boy. Let's make this. Let's make it a bigger matrix. K, K, minus K, minus K. These are all K1s. And so we included the node that wasn't included already. So there's a Q3 in this problem. It's not included in here. If we include it, we have to recognize that for element 1, that doesn't have anything to do with node 3. So we just have a 0 row, a 0 column, and 0 on the right hand side. And then we did the same expansion over here. We had a 0 row at the beginning, a 0 column at the beginning, and we had K2, K2, minus K2, minus K2, Q1, Q2, Q3 is equal to 0, F12, F22. And then now we had them in this format, we could add them together. This was to produce the global problem. So K1 minus K1 and 0 minus K1, K1 plus K2 minus K2, 0 minus K2 and K2 is equal to Q1, Q2 and Q3. No, sorry, it's not equal to, that's the vector that we've got to multiply by. So let's see if I can move that. This is a multiplication now, I've just drawn those a little bit too close. F11, F21 plus F12. And then we recognise that these are all the forces on the system, so if we add them together, these have to be equal to the global forces. F1, F2, and F3. And if you're a little bit confused about this step, we could just recognise that if we were to draw a free body diagram of that central node, then the forces that we would see present are these local forces, F1, 2, F2, 1, and these have to be equal to F2 in this case. That's just the global force. These are these local forces that are applied. So this is problem, global stiffness matrix, global displacement vector, global force vector. And we set this up for this problem, and we then went ahead and solved it. I've just noticed a mistake in the notes. It's very minor. I said in the notes, I said that K1, K2, I gave them values of 50 and 75 pascals. That's the wrong units. Stiffness has units of newtons per meter. So I could have put Pascal meters, but I was wrong. It should be newtons per meter. Okay, so let's say in the example we had K1 was equal to 50 Pascal meters, and K2 was equal to 75 Pascal meters, and we said F2 was equal to F3, 7.5 newtons. So make sure that you go through and understand how we did that solution, how we went through it, because I'm going to ask you to do a homework on this. Because the next step that we want to look at is we want to be able to use this methodology to solve for truss frames. Now, truss frames don't comprise spring elements, they comprise bar elements. So how do we change this methodology that we've applied to account for that? What about bars? I miss bars, and I can't wait for COVID to be over when we can go and enjoy them again. But these sorts of slightly less interesting bars, let's say we'd looked at this problem and we had different bar elements on here. Rather than spring elements like we had here, if we had bars, we would want to use the same methodology to solve it. And again, just looking at this problem here, the bit that I hadn't mentioned was that the only way we could solve this problem was by enforcing the boundary condition Q1 is equal to 0. So if we had this problem here, let's say we've got same sort of problem. We've got forces applied to a system. We've got two displacements that we'd like to determine, Q1 and Q2, and we've got a bar element with a cross-sectional area of A1. This one has a cross-sectional area of A2. They've both got the same Young's modulus, so they're made of the same materials. And then they are two different lengths. We've got L1 and L2. And here, now this brings us a little bit closer to being able to use the formulation that we've got to solve for truss frames. Now, when we had a spring element, the stiffness matrix, just the element stiffness matrix, took the form K, K, minus K, and minus K. Okay, so when we know the value of K, we're able to formulate those two element problems that we did previously, work out how to expand the matrix by putting rows of 0, columns of 0, adding them together and solving for these two displacements, Q1 and Q2, and then also solving for the unknown F1. If we've got a bar element instead, we've got a very similar stiffness matrix. So let's say if we have a bar element instead, then our stiffness matrix is 1, 1, minus 1, and minus 1, but we pre-multiply it. Well, since it's a scalar, it doesn't matter whether we pre or post multiply it, but Young's modulus, cross-sectional area divided by the length. Okay, and the units of this are the same as what the stiffness should have been, which is Pascal meters, or newtons per meter. So remember, E has units of pascals, A's got meters squared, L's got units of meters. So this gives us PAM, or newtons per meter. Okay, so this is how we've changed the problem to set it up for bar elements instead. So what that means is that now, if I were to give you a problem, and I am giving you this problem as homework to be handed in on Sunday nights, let's say we've got, I'm going to draw them just as we would have drawn for a truss structure now. Let's say we've got nodes 1, 2, and 3. This has got corresponding displacements, Q2, Q3, and Q1, which has to be 0 because this is a built-in here. We've then got forces, F2 and F1, F2 and F3, which could be applied, and then we've got the reaction, F1. So I want you to take your student numbers, say A2's at 203, 1, 2, 3, 4, 5. Student numbers all look something like this. Okay, you've all got roughly the same first 3 digits. You've then got 5 digits afterwards. So your first 3 digits are your E in gigapascals. Okay, so you're either going to have 203 or 204, or maybe a few, you might have 205 or 202, but you're going to have that will be your Young's modulus for both of these elements in pascals. Now, these next ones, so the next 3 digits, that's your A1, and the next 2 digits, that's your A2, okay, and these are in cm squared, in square centimeters. If there is a leading 0, or 2 leading zeros perhaps, to either of these, stick a 1 in front of it, okay? So your A1 or A2, what do I mean by that? Well, if your 2 digits come out, and you happen to have, say, 0, 7, you're then going to have 107. That will be your A2, okay?
trying to be as clear with this as I can. It should be relatively simple instructions. So your A1 and your A2 are going to be different for this problem. Let's say L1 is 2 meters, L2 is 1.5 meters. Let's say F1 is 1 kilonewton, and then F2 is your last 3 digits in kilonewtons. No, your last 3 digits in newtons. Last 3 digits in newtons, let's call that. And again, if you have a leading 0 or 2 leading zeros here, I don't think anyone's got 2, are frozen. Let's just try and unfreeze my camera. That would be good. Okay, there we go. Right, so if you, this is your last 3 digits will be your force 2. Oh, sorry, I've messed it up, haven't I? Let's say this is F2 and F3, rather. Okay, so force 2, which is going to be this one here, everyone's going to have 1,000 newtons. F3 is going to be your last 3 digits in newtons. Okay, and again, if you have a leading 0, put a 1 in front of it, that's going to be your force there. I want you to take your inputs, which are defined by this problem here, and what I want you to produce is show me the governing matrix that sets up this problem, that solves this problem. So you've got everything to determine your individual stiffness matrices for each spring element, they're now each bar elements, and you then know to go through the same procedure we went through before, where you take each matrix, write it locally, expand it into this format, add them together, get your global system. Okay, so you've now got enough information to do that. So I want you to be able to show me what this looks like. I then want you to, by utilization of the correct boundary condition, which is that Q1 has to be equal to 0, solve for unknowns, and these are Q2, Q3, and F1. Okay, and then demonstrate from first principles that F1 value is correct. Okay, so set your problem up, show me what your matrix problems look like, your matrix equations look like rather. I then want you to solve for the unknowns in this problem, and then want you to go through and demonstrate from first principles that your value you get from F1 is correct. Now what do I mean by that? Well, when we solved this previously, I drew a free body diagram at the beginning and I said I know what my F1 has to be. Then went through and solved it, got what F1 was, and showed that I got the correct answer. So that's what I mean, but you guys are just going to do it in the other step. So how do I want you to formulate this? One PDF, let's say all of your answers I want on a single PDF sheet. In fact, you shouldn't need anything more than a single PDF sheet to show this. You can maybe show an additional page of working if you want. You start putting 7 pages of working on a problem like this, then it just shows me you guys don't know the correct amount of stuff to submit for work. Okay, so a single PDF sheet should contain all of your answers here. If you really struggle to get, and you want to show your element stiffness matrices, I'll accept an additional sheet, but anything more than 2 I'm going to ignore. Okay, so single PDF sheets plus a possible additional sheet if you want to include any working, but you shouldn't need it. Okay, you should be able to succinctly describe every step of this problem in 1 page. and this is to go on Blackboard by Sunday. I think it's the 29th. Let me just check. No, it's the 28th. Okay, so hand it in by the end of Sunday night. Get it on a Blackboard. This is not a long problem. If you followed the last lecture, you should have. So if you followed the last lecture, you should have notes on that already. You should have followed along. You should have been going through it. Okay, if you haven't, you've got to go rewatch it or just watch it for the first time. And as you're doing this, go through, understand, and then afterwards, just spend a bit of time making sure you follow what we've done. Okay, these are the steps that I would expect you all to be doing. Prospective aerospace engineers. Okay, this stuff isn't supposed to be easy. You have to put this sort of work in. You've got to do this sort of work behind the scenes to show that you know how to do things. Okay, so get this done. I'm going to go and record one more lecture on how we now take this problem and expand things for looking at real truss problems. Let's just think about what we can do so far. So I've just shown that we could solve this sort of truss problem like this using the method that we've got. Haven't actually done an example, but I've given you everything you need to do to go through an example. Okay, the only thing we haven't done, I haven't shown you how to multiply E by A divided by L and get a number. Okay, that is just scalar multiplication. I'm sure you guys can handle that. So we've done this, we've shown how we can do this. We couldn't yet solve this sort of problem, okay? And that's because we've got angles involved. So this element here, for example, is not aligned with this element here or this element here. So we need to think about a means we can solve for that. I'm going to stop now because they're about to pull the bins past my condo and it gets very, very noisy. See you guys in my next lecture.